Hey, we're going to do a trig substitution integration problem here. The problem is the integral of the fraction numerator square root of x squared minus 25, denominator y cubed. That's going to be integrated in terms of y. So we see the square root of y squared. So it's a variable squared minus a number. So that's going to be a certain type that I usually use as x squared minus a squared. So that's why I have the little template over here that I'm going to use. So let's look at all the parts we need here. We need to figure out a name for square root of y squared minus 25. And please note in there that the a squared is 25, so the a is 5. So down here I have a tangent equals the square root of this thing. So this will be 5 tangent of theta. Now the next thing I need is y cubed. My y is the same thing as my x, and x is a secant, so that would be 5 secant. So y is 5 secant theta. So y cubed is 125 secant cubed theta. And then based off of what y is, the dy will be 5 secant tangent d theta. So I've connected all these parts together. So let's see here. We've got the square root part, which we have. We have, in this case, the dy part. And we have the y cubed part, which comes from the y, okay, in this case x. So while I'm here, I'm going to go ahead and draw a triangle, just in case I need it later. Let's draw it up. Well, let's draw off to the side because I think we'll work down. So we'll make it look like the triangle in our template. So theta and the right angle. So the base is 5, that's our a. X is y, and the opposite side is y squared minus 25. So if we ever need to go back and build a trig function based off of an angle, or if we need to do an inverse, we have all that information visually ready for us. Alright, so making these substitutions, let's see, we'll have the integral of 5 tangent theta on top. On the bottom where the y cubed was, we'll have 125 secant cubed theta. And then we're going to place the dy with 5 secant tangent d theta. So as we clean that up, we'll have 25 on top, 125 on bottom, so that'll simplify to just a 5 on the bottom. We have 2 tangents on top, so that is a tangent squared on top. We have a secant on top and 3 secants on the bottom, so that's a secant squared on bottom. So we've got tangent squared over 5 secant squared. I think we probably need to work on this by changing everything to sine and cosine. So tangent, so let's just put the 1/5 out front. So tangent squared would be sine squared over cosine squared. And we're going to divide it by secant, which secant is 1 over cosine. So secant squared is 1 over cosine squared. So we're dividing by that. So a keep change flip would put that cosine squared on top. So I can cancel out the cosine squareds, and what I'm left with here is a 1/5 integration of sine squared d theta. Now this is where we have to go back to our trig powers. So we turned this into a trig problem, but now that we look at it, it goes back to a trig power problem. So remember that if we want to change a square, at least a sine squared, that changes to 1/2 minus 1/2 cosine of 2 theta, if I'm not mistaken. Okay, so we'll have that 1/5 out front, and then we'll have the integral of 1/2 minus 1/2 cosine of 2 theta d theta, which we can't integrate. We'll have the 1/5 out front. The integral of 1/2 in terms of theta is 1/2 theta. And then the integral of negative cosine is negative sine. So we're going to divide by the 2 inside. So I'm doing a little u substitution. So it's 1/2 divided by the 2 from the inside, sine of 2 theta. This will be a plus c. So I didn't write out the entire u substitution there, but if you went back and took the derivative, you should get back to where you want to be. Now I got a couple things I got to do, because I don't want to leave this thing in terms of theta. So let's just kind of rewrite one more time before I go back. Clean it up a little bit. So I've got I'm going to distribute the 1/5. So I've got 1/10 theta minus 1/20. It's a sad looking 20, so we'll fix it. Sine of 2 theta plus c. So we have a couple things we need to do here. One is we need to figure out another name for theta, which we can do in terms of y. But before I do that, let me look at this trig function, because now it is sine of 2 theta. Well, our triangle does not have the angle 2 theta, it just has the angle theta. So let's just keep everything in terms of theta for a moment. 1/10 theta minus 1/20, and there's a property that says the sine of 2 theta equals 2 sine theta times cosine theta. That's a trig property we've used in the past. So we'll rewrite that. So this is 1/20 times 2 sine theta times cosine theta plus c. Now let's work on putting this thing back in terms of y. So we got the 1/10 and we want theta. So I look at this thing, I can use any trig inverse that I want, but I notice I have a adjacent and hypotenuse, so I'm going to use a cosine inverse so that I don't have to use the square root in here. It really doesn't matter if I use the square root or not, but 1/10 cosine inverse of 5/y. And then we'll have minus, and we've got 1/20 times 2, so that'll be another 1/10. Sine of theta is opposite over hypotenuse, so that'll be square root of y squared minus 25 over y, times the cosine of theta, which will be 5/y plus c. So let's do one final cleanup here. The first one we're going to leave alone, and you could have a different trig inverse function here than cosine. You would have a different argument inside the inverse function, but let's just say you have what I have. So 1/10 cosine inverse of 5/y, and then we'll have minus 1/2, and it looks like square root of y squared minus 25 on top and y squared on the bottom plus c. There might be some variations we could do there, but it looks like we've completed the problem the best we can. Thank you.